Okay, hello. This is the last week. Congratulations, it's week 14. And again, we have additional information about heat loss and heat loss calculation that hopefully you will be able to use to your advantage when you're preparing for your project and also when you're preparing for your uh, heat load analysis exam. Again, the science has not changed. This book is from the 60s. Probably some factors have changed. The material probably are different, but the bases are the same. You might just need to add some insulation for some parts and add some installations or like updated material which you can look up in Google. So I will go walk you through the heat loss calculation guide and comment on what can you find that will be helpful to you. And actually, this book is very small, but yet it's very rich of information. So it start again. I don't know. It's the new version of 2001, but the book has been revised so many times, and it's still in use. Really, really valuable book. Let's go through it. I'm gonna go through it page by page. Contents. They talk about heat, the human comfort. Look at that. We talked about that before, which is heat comfort. What do we mean by that? So 70% is kind of standard heat temperature. Some people might prefer 75, but 70 is a standard, not 75. And you can go down to 65 if you want to. And you can add 20% and heat the house a little bit more, but it's not that necessary. And they also talk about heat here and BTU. What do they mean? And what else? Also, the heat flow from hot to cold, and so on. So it's always going to change. And sorry, heat loss. Heat is always going to move from hot to cold. And let's see what happened here. Okay, hold on. Okay, erase and keep moving. Okay, heat loss, heat flow. Why do you need heat loss? They tell you it's about fuel economy. You want to make sure that you size the boiler correctly. And again, load versus boiler capacity. And what is this? Part load efficiency. I'm gonna make it a little bit bigger. So you want the efficiency to be somewhere around here. So the more you have the load meets your efficiency goes over here. This is the curve, and part load efficiency is over here. I don't know what exactly they mean by that. Hold on. Based on typical boiler with 80% steady state efficiency. Okay, so what they are trying to get at is that they want you to design the load to be based on how much you consume, so you do not have a lot of off cycling. Moving on, infiltration losses, we talked about that, and about porosity of the wall and with holes in it. So, and this is the method that they use. It's not necessarily the only one. There's so many ways to calculate heat loss through infiltration and calculate the CEFM. If you look here, the infiltration heat loss factor in table 2, that's at the end of the book, is exchange per hour. That's 0.012, which is two-thirds air change per hour. What does that mean? That means you are going to change two-thirds of the room air inside the house in 1 hour. 0.08 is one change per hour, so it's a little bit higher, and it gets higher and higher, meaning the entire volume of the air inside the room will be changed within the hour with these fractions. So this is how they are measuring the heat loss for that room. So the infiltration heat loss factor represents the BTU for every cubic foot of room volume for every degree Fahrenheit difference between indoor and outdoor temperature. So again, this is how we calculate that, the factor, volume, temperature difference. Here are some notes. Windows not weather stripped and without storm sash, they have, again, more heat loss than the one with storm sash and weather stripped. Okay. For the transmission, we are concerned with surface area. because again, this is the factor. I cannot switch it. I usually say Q equal A times U times delta T. It's kind of the same. So there are reversed. U is the factor, and surface area is the area that's exposed to the outside. And they give you the table 3, and lines and all the capacities. As a rule of thumb here, they say shortcut methods, procedures, does not take into consideration material and construction of details of the wall, ceiling, and floor. So these are a ballpark. They're not necessarily what is actually existing on the wall. So it will be very beneficial to go and examine the wall yourself and see how thick it is, do some measurement, what's inside the wall, what's the siding, what is the in the inside. Sometimes even wallpaper does make a difference. So that's something you have to consider a little bit in the heat loss. And again, it does not mean that you have a bigger boiler, it's better. That means that you have a lot of cycling, which is not good. These are the steps that I went over last week, and summary of the steps: find the design temperature and number the rooms, dimension. That's something you get by measuring or looking at the floor plan. And again, always approximate to the quarter of a foot to make things a little bit easier, because again, 1 foot is 12 inches, and you can get 1 foot and 2 inches, so you don't know how much of a foot is that, so you just go with the nearest higher quarter of a foot to make life a little bit easier. The imperial system for measurement is a little bit awkward, but we have to live with it. We're doing filtration, transmission heat loss, then the total heat loss, where we add everything. Again, calculator, or you can use the Excel sheet that I provided you and the week material, and floor plan for the building, and building construction material. This is going to be a little bit difficult to find most of the time, but and sometimes you have to go and guesstimate it. Luckily, everybody now have an iPad or a phone. You can go there and Google the material by name and see what is this wall R value. Knowing the R value, you can get the U factor correct, or you can get multiple R values or R value per inch, and you can add them together and find the proper insulation. You will have fun doing this because it will make a big difference when it comes to saving energy and changing the numbers. So then you need the form, which they provide at the end of the book. You can cut it or photocopy it or make your own, or use the one Excel sheet that I gave you. So this is an example. It's called R1 residence. They took the information here. It's in Belling, Montana. The outdoor design temperature is -10. That's from table 1. That is very cold, and they designed for the coldest extreme day in the last 10 years. So this could actually have been changed in the last 10 years. The walls, they got the walls. They assume the walls are all like uniform and they have the same heat loss. Same with the ceiling, windows, and they decided that the garage is unheated and the attic is unheated, so we're going to lose heat from those two spaces, and no plan for use. So it's not going to be used, very small, so it's unheated, no plan for use. So we would need to put some insulation in it. Let's look and see how well did they do doing this. The basement is also unheated and has concrete floor, etc., etc. And do they say that if they want to heat it or not? Let me see. It does not show that they want to heat it, so I guess it's an unheated basement. This is the floor plan. If we look closely, we see all the dimensions here for the walls and the windows. So this window is 3 by 2, and 6 inches is the thickness of that window. I don't know if it matters that much, but that's what you need, is the 3 by 2 width and height of the room, and also the ceiling height. So this information is what you need, and you can draw that sometimes from a plan, from a house, without even have to have your own floor plan. And this is the basement, which has some windows in it, but again, I don't know if it's heated or not, but the basement is mostly below grade. That's how this is when the below grade and above grade part comes in. So you're going to lose heat to the wall or the slab below grade, and you're going to lose heat from the top over here, and you know that always heat always rise. So this part is going to be hotter than the part at the bottom. So design temperature difference, we got that. So inside is going to be 70, outside is going to be colder, and we said it's going to be -10. So here, oh look, these are the design temperature came from the 1980, so that's 40 years ago. That's completely has changed. Okay, so let's keep that in mind. And again, when in doubt, you can always Google these things. Outdoor design temperature, we got that. design temperature difference, that's inside minus outside, yada yada. Here we go. And here is how they go through the figure and fill in their room in the table. Hopefully they have the same thing here. You can see the tip of the table where you put in your length, width, and height. So you record that for each room, and you put the temperature difference inside and outside. The reason they keep that different form for each room is because you might want some rooms to be hotter than others. That's based on personal preference and how do you use it. So we have a temperature difference of 80. That's a lot, okay? And also it says add 20% for bathrooms. I do 15%. It's not going to be a killer, but between 20 and 15% is reasonable. Okay, so this is very cold. We're going down, and room dimensions. So length or width depends on on the orientation of the room. It doesn't really matter this much. And we have the height. So the height is from the floor to the ceiling. Room dimensions. Again, always get closer to 1/4 of a foot to make things a little bit easier for you and make them more convenient. Okay, we got that. Okay, here is the sheet that you will find at the end of the book. And if you look closely, this information is very useful. Look at the dimensions and look at the notes that tell you. So the infiltration, they tell you where to get the infiltration rate. They tell you where to get the ceiling height and the information, and length, width, and temperature difference for each room. And you just fill in the blanks in here. And if you use the Excel sheet, it will fill itself if you just do the top, and you can fill the factors, and you will see the difference between wall type. One thing you have to consider is when you do the wall, take out the window. Do not include the window because that will add to your wall area. Sectioning. If I'm doing section of the house, I really don't care much about that. It's optional. So if you notice here, this area is not going to be heated, and they will heat this bathroom. If it was me, I would not heat this bathroom. I might put a hot floor, but again, it's a preference. There is no one solution, one answer. But this has to be, anything to the outside has to be heated. The inside is optional to heat or not to heat. So they put the measurement, all the measurement they have for all the rooms, bathroom 1 and 2. Where's it? This is 1 and 2 over here. So you have two bathrooms, one bedroom, bathroom 1 and 2, family room, kitchen, bedroom 3 and 2. Okay, infiltration. It's again factor, volume, DTT, and getting the factors. Again, factor is the number of exchange, complete exchange of the volume per hour, and you find that from table 2. And let's look at this, finding the factors. Look at this information in porous wall construction. Be sure to check whether the wall construction for the room is covered under the porous construction listing in table 2, filtration heat loss factor. So some walls are very porous, like if it's a log cabin or something like that, or hollow concrete walls, they are very porous, and you get a lot of heat, a lot of infiltration going through them. So that's something you have to pay. Okay, so record the factor and dimensions over here. Okay, now looking at again example, filtration still for each room. So again, how do they take the factor for each room based on the sides where you have walls? So this is actually very good explanation here. If you look at this room, you have 0.018 because there's only one side with the room with the wall with space to the outside. Actually, there's two, and this in here they included the entry hall to it. Over here you have 0.012 because there's only one side with a window in it. What about this one? This is 0.018 because there's two walls with with two windows in them. What about this one? It has two windows and only one side. Still going to be 0.012, and the hallway will get the big infiltration because you have a door to the outside, and the air is gonna gush in here whenever you open the door. So we designated all these heat loss for this heat infiltration factor for all this house. So now we move to the transmission. Again, transmission is heat going through the ceiling, floor, and walls. How explanation, we've been through that. Heat loss factor, we did that. And again, this is how it fills up little by little. The volume is for this. The first part is completely just infiltration, then ceiling, floor, slab, if you have it, and windows and doors. So you fill in the factors from the book and the areas, and the DT will be the same. So they did that for the room, and they talk about construction here. So, oh, okay, this is good information here. So ceiling exposed or to an unheated space. That's different than a roof, because the ceiling is going to leak heat to a space that is not heated, but it's not the outside, so it's kind of different. So it has different heat loss factor. Floor exposed to unheated space, that's again different. So whenever unheated space is different than a crawl space or a ventilated basement. So whenever we have ventilation, we have colder sides, and also cold partition. All those three are the same, which basically we're losing heat, but not to the outside, to a cold space or cold partition. So that's a little bit different. So as they say here, hold on, let me fill up the writing. Uh, so one side will be significantly lower than the normal temperature. On the other side are considered cold partition, but they're not considered to the outside. So it will have a heat loss, but not the same, and probably can take down a few degrees from the colder temperature outside. Again, that's all so you do not oversize your boiler. Windows, doors, we did that before. Exposed wall, that's something going to the outside completely, and it has uh, their own tables. Ceiling, area of the ceiling, uh, insulation, U factor, partially exposed ceiling, you're gonna have to do two areas for that. So it's only the area of ceiling below unheated space. If it is possible to have a portion of the ceiling under a heated space with remainder exposed. So again, if the ceiling is partly heated and partly unheated, you're gonna take the part that is unheated. Because if it's heated in here, we're not losing heat to this area, but we might lose heat in this area over here. Expandable attic. Floors, the same thing. Wood floors, you calculate the area of the floor, heat loss factor. Crawl space, again, there are special cases. They're not always the same. So overexposed areas such as cantilever extensions. So there's nothing underneath but air. Crawl space, if the crawl space is enclosed and ventilated or exposed, make sure the pipes in the crawl space are also insulated. That means really cold. Over crawl space, if the crawl space is enclosed or not and not ventilated and heating pipes are insulated. So these are all going to be part of the heat loss, and the temperature will be as if it was outside. So this is when do we calculate the heat loss, or when do we not do that? Concrete floor, they have a different heat loss to the floor, and here are the cases. So go over them if you're going to heat the basement. Windows, we know a lot about windows. Jealousy windows are, I don't know if they're common anymore. They're kind of like blind windows, single pane, kind of like slates, and they open and close. And I don't know why they call it jealousy window. I think it's a French name. It's not because it makes people jealous. I don't do with that. So storm sage is strongly recommended for these windows to reduce the heat loss. Where storm sage is used with jealousy windows, use infiltration factor for windows without storms in order to account for the high leakage through these windows, in case you have some of these. For the windows, you're going to go with the area of the window, not the frame. Type of windows. This is jealousy window. Doors. Again, we're only heating doors to the outside. Inside doors do not count. Exposed wall. And here is the table being filled up. Little by little, it's getting full. And you can see all the information are in it. Walls below grade, that if the wall is half to the outside and half is buried, that's below grade. And cold partitions, so let's see about wall below grade. Walls 2 feet or less below grade are treated as exposed walls because the ground provides very little insulating effect, and the ground temperature will tend to track outdoor temperature. So 2 feet or less below grade is going to be considered as completely exposed because the ground is also cold. The transfer of heat through the basement wall floor for more than 2 feet is dependent on temperature difference between the air inside and the temperature of the ground, also on the material constituting the wall or floor, and the conductivity of the surrounding earth. The conductivity of the earth will vary with local conditions and is usually unknown. Interesting. If you have a basement, that's going to be very difficult for you to know what is the heat transfer to the wall. But if you have a basement, I highly recommend that you have some kind of fake wall or dry wall and fill it with insulation and vapor barrier, because you get a lot of moisture from the ground as well. Check this out. So the factor for heat loss wall floor below grade have been adjusted by multiplying the calculated U factor by 85%. That's a lot, to compensate for the fact that the ground temperature is higher than the air outdoor and the full design temperature difference marked on the upper left from the table. So if you think about it, conduction is the strongest mode of heat transfer, and instead of you having convection to the air outside, you are conducting to the ground. So you lose heat way much faster when it comes from the ground then to the air. So that makes a lot of sense for wall below grade. Cold partitions. Let's look at that. Walls not exposed directly to the outdoor temperature, but adjoining unheated room. These cases are treated separately because the outside wall is not exposed directly to the outside temperature, but the temperature is in the adjacent space is cooler than the design temperature. That's kind of like the Porsche that we have from last week. The Porsche is cold, but it's not completely outside. Garage, Porsche. What do we have here? We have some cold partitions. So what are those considered? So for these, they have their own U factor. So it's called cold partition here. U factor have been adjusted to full. DTT can be used when calculating the heat space through these walls. So you can either use the adjusted U factor for the cold partition, or you can use it as the outside. I rather to err on the side of cautious and just put it as the temperature outside, or you can take a couple of degrees out to compensate for it not being as cold as the outside. Basements. If you're going to heat the basement, you have to look at the slabs and the walls and the heat factors. There's a special case for that, and there's also some windows with infiltration in it, and it's below grade. So that's for the basement. This is the whole thing about the basement. No ceiling for the basement. Infiltration coming from the walls. Okay, calculate the infiltration volume using 1.5 feet as the height. So the volume for that infiltration, which is very interesting, is not going to be the entire volume of the basement. It's going to be the volume on the top, like this volume over here only, not the bottom volume, because this air is going to be settled and hot air rises. So that's very interesting. As height, see the construction over here, and the rest is going to be has nothing to do with the infiltration. Okay, it's going to be 0.018 for that complete row. Interesting. Ceiling, no ceiling, because again the floor is heated on top of the basement. The floor is going to be slab, completely slab, and for here there's the slab section for that area. You're gonna get the area. So locate the factor for concrete floor more than 2 feet below grade in table 3, section 27, line D. The factor is 0.04. Enter this value on form 1504, which is the form over here. And if you check out something, okay, let's look at this here. Slab, I want to show you something. Hopefully I can show you. It's here. Window area, wall, floor. Doesn't show. Okay, I will look at. I will show it later. Walls. Hold on. I'm gonna look at this very closely. It's It's really hard to see. So the factor area base. So the basement has its own thing. Volume. We have the volume for the infiltration. Temperature. No area for the walls. And this is doesn't show. Slab area. Wall area. We got that. Minus the windows. Well, something about the perimeter. I think it's going to come up later on. I'll show you. Step 5, filling the table. You multiply everything together, then you add it. Adding the total heat loss for the building. Special application. Let's look in here. Garage, doors, basement, concrete strip. We have, this is the factor. So we have two factors, something above grade and something below grade. And the windows are considered weather stripped and insulated. Okay, heat losses. Moving on. So the main floor, including the basement, was 48,000 BTUs per hour for both infiltration and transmission. So okay, here, let's look at this. Basement, bedroom 1, bedroom 2, kitchen, family room. So they're giving you an option for the basement in here. And 2 of 2, entry hall, bedroom, living room, basement. Let's look at the basement. I want to see what they do for the slab. Because there is no slab for the floor. They use the factor of basement floor and the area of the walls, and no ceiling, of course. And for walls below grade, these are the total walls. Okay, so they divided the walls for above grade and below grade and use different factors, which make sense. Okay, we got that. What are they talking about here now? Oh, whoa. Special factors, okay. So this is how to calculate your own heat loss if you own U factor, if you have a composite material. So if you keep adding onto a wall, how do you add your U factor? We did that in week 2, and we said U factor is 1 over R, and you keep adding all these values. We did a homework about that, so I think we're good in this example. So total R, you add all the R values together, you get the R, then you get the U factor. So we did that. And here we have a lot of insulations and R values or thicknesses for many kind of different material, and you'll have actually some in the residential energy book as well. More factors, and let's look, what is this? Transmission factor, stud correction factor, okay, another U factors. Heat losses for special cases. This is if you have a fireplace, how do you accommodate for that? Cathedral ceiling, greenhouses, log cabins, cold partitions, and mechanical ventilation. Let's touch base on these. So if you have a fireplace, how would that affect your infiltration? There's bricks, there's chimney. There's a heat loss example here. Actually, it gives you the heat loss factor. Okay. So this is a heat loss through the fireplace. So it has its own heat loss, and here's an example for the size of the fireplace and the heat loss through that. I'm sure it's a big infiltration loss because again, it's designed to pump in hot air to the outside, and there's a factor to it as well. Okay, cathedral ceiling is what we did in one of the homework. Actually, it was in the midterm where you calculate the volume of an attic. That's triangular, so we did that already. And here's another example about that as well. Skylight is going to be a window thing. It's not going to change as much as infiltration or transmission. And what they're trying to see here, if you have a cathedral ceiling, how would you account for that as heat loss. You will just get the area for this part of the ceiling and calculate the heat loss through it using the R value. Greenhouses, there are glass. I'm not going to go through this. We can skip that. Log cabin, different wall insulating material. Cold partitions, we did that already. So for cold partition, you get the heat loss factor, then you get the correction factor over here. So sometimes it's the same, sometimes it's not the same. I will just use it as the way it is. It will be a little bit easier. Mechanical ventilation. That's really interesting. So that's something you will add to a house whenever you have mechanical ventilation where you are exchanging air all the time. So again, 1.08, that's the equation we had, CFM and 70 degrees to give you the BTU. And if you have a mechanical ventilation of 50 CFM, which is for 3 people at least, or 4 people, that's 4,000 BTU an hour, which is not that much. So you're better off just add that to your heat load as well. 50 CFM. Outdoor air conditions. This is some correction factor for degree days. So that's the table. The main intention for this is to explain to you how to calculate this whole thing. If you want to go through it, is to calculate the annual fuel utilization efficiency and how much you can estimate how much oil or gas are you going to need for the entire season. It's a very good example to size your tank or size your gas tank or oil tank and see how many times you have to fill it. So it's a little bit involved, but all the information is available for you. And the degree days, okay, let's look at this equation here. Estimated annual fuel usage. This is the heat load over here that we calculated over 24 hours a day. So we're doing this for 24 hours, not only 12 hours, times the number of degrees. Degree days you can find also in the table where you found the temperature outside. So they give you the degree days, which is the number of degrees you're going to heat that house for the entire year. So this is the number of degrees, 24, and over here we see is what, 0.63. That is the correction factor depending on the degree days, because again, I guess they are assuming that in here you are not going to heat for the all days, so there are some correction factor for that. You add this in here and you divide by 0.038 efficiency for burning a gas. And if you have gas, if you have fuel, it's going to be different. And the Q is the heat quantity for therm of natural gas. If you are using oil, it's going to be different. This is oil, 138, and this is for gas. And annual fuel, AFU, that's the efficiency of the boiler, which is 0.83. And finally, 80 is the degree days, and this will give you the amount of gas you will use for that house in a year, roughly. And that's kind of like having the MPG on the car, but this is the MPG for the house. This table you already used, where you find all your towns and Massachusetts. We have here, hold on, let's look at Springfield, Westover, 0. This is the coldest day of the year, and 5,840 is the degree days, amount of degrees we're going to increase that house in temperature for the entire year. So Boston is a little bit warmer than Springfield, and the coldest is Pittsfield, which kind of makes sense. And okay, most of the towns, and again, these things you can find online as well. Heat loss factor, infiltration, transmission. Give this a skim because they're very important to know where these things are located. What else? This is the table you can print out and fill in the blanks. You can have more than one sheet. Some of the material you can put in the back of the same sheet as well. Extra one over here. And that's it. That's the entire book. It has whatever you need to do a heat loss calculation for the entire house. Before I go, what do you think its difference going to be if you're going to design for cooling? That's going to be a little bit different, right? Basically, you can use the same exact material because the material is going to be the same, but for cooling, we'll change the temperature difference because cooling is going to be for the between hot inside and cold outside, and temperature will move from the inside to the outside. So it's going actually from the outside to the inside. So it's going to be a reverse. So you'll use the same Excel sheet, the same table, you will just change the DT number in here and everything else will be the same. And you might add things inside the house that emit heat, uh, but you'll have the same mechanical ventilation completely. So again, if you did the heat loss and you did it in the Excel sheet, you can just go with one click and change the temperature difference and everything will be calculated for you. All right, thank you, and let me know if you have any questions, and I'll open the discussion board for this week to see if you have any questions regarding the heat loss. Thank you.